Week 14, Part 4, Single Slit Diffraction. So here is the ripple tank again with just a single slit. You saw this before. When you have just a small opening like this, the waves come out almost hemispherically here, almost uniformly all the way around. But we'd like to see what are the effects of that slit itself. It isn't exactly perfectly uniform. And what happens if we make the slit wider? So let's take a look at that. Here is an example of a slightly wider slit. And if you look at this, it's already starting to do some weird things, but the thing to notice is that the center region is now stronger and the sides are weaker. So we're getting more straight through the slit and less off to the sides. It's hard to get this to work properly. Exactly. When I make the slit wider still, some problems creep in because the source isn't very far away, and so the waves coming in here are already curved a little bit, and that changes things. So what I've done is created one in which there's a lens right here, and after the lens, you've got plane waves if you put it at the right distance. So you can kind of see that right there, it looks like nice flat plane waves coming to a very wide slit now. Now, if you look at this slit, I think you will agree that there is a large, strong central area here where the waves are coming through quite strong. And then if you look on either side of that, I think you can see a kind of region of cancellation over here and over here. So there seems to be almost nothing getting through at that angle. And then all further, it's there's some intensity again, some waves that are sneaking out even further. So how do we explain what's going on here? Well, let's look just again to see what you would really get. If we made this slit wider, this central area would just become narrower, and these minima would come in closer. So let's take a look at an example like that. So this is the sort of a picture we've been looking at, with a really wide central maximum, and then a minimum right here, and then a little bit of something on either side of it. A little hard to see exactly what. This isn't the best example, but that's with a fairly narrow slit. As you make that slit wider and wider, these white regions are showing you the opening. And as you make the slit wider, especially with something like light, you have to do this with very narrow slits indeed. Even these diagrams are not to scale. These slits, as they get wider, this pattern gets narrower. Central area gets closer and closer together. And you see more and more of these little ghosts on either side. Eventually you see a whole series of them. And these minimums get closer in like this. So what in the world is going on? How can we understand this? Well, we can get the beginnings of an understanding by looking at this diagram. See if you can understand what's happening here. So here the red would be the wave fronts coming along. Blue would be sort of like rays, if you like. And now, right when the wave front sort of arrives at this point, we've got all these little ripples forming. And we can then trace to see what happens at some very distant point, very far away. So these rays are going to be essentially parallel. And see, how do the ripples from each different point on this wave interact? Now I know this seems strange. You wonder, well, wait a minute, how does the wave suddenly turn a corner there? Why would it do that? Well, that's the Huygens construction always. You draw the wavefront there, and then each point along the wavefront becomes a source of a little ripple. I've only drawn a certain number. There really would be an infinite number of those. And normally they tend to add up and sort of recreate the wave and keep it going forward. But there can sometimes be other directions. You can draw a line here that connects this ripple with the second ripple from the next one and the third ripple from the next one and so on. So you can get a direction in which you get a maximum off some way. The trouble is, if you were to change the spacing, that wouldn't work again. But there is something that does work, and that is to look for those minima. It turns out there's a very simple explanation for those minima, those angles at which we were getting nothing. If you look at simply one of the middle rays, one of the rays coming from right in the middle of the slit, and compare that with a ray right at the edge of the slit, when there is a minimum, that corresponds to the situation where those two rays are exactly half a wavelength off. One of them is shifted. Remember, the one has to go a little further, and so there's a little triangle we can draw here. And that's what I'm trying to represent here. This is essentially that same triangle. So this one has had to go that much extra. If that's exactly half a wavelength, then these two will be out of phase. Now the others won't. They won't be out of phase with this. In other words, this one right here won't be out of phase with that one. But if these two are out of phase with each other, then the next two will also be out of phase. In other words, this one will be out of phase with that one. And we could pair them up all the way down the line. If we started in the middle with a ray in the middle and one on this edge, then we can pair them up all the way down, and every one will be paired with one that's exactly out of phase. Now, they don't come in that order, but it doesn't matter. They're all being added together in some sense. In addition, you can rearrange the order all you want. So we'll rearrange the sum and we'll say, look, when we add these together, this one plus that one is 0, this one plus that one is 0, and we get 0 all the way down the line. So when does that happen? Well, the distance from one of these in the middle to the edge, that's the vertical distance, the hypotenuse of this triangle. That would be half of the width of the slit. We usually give the width of the slit as the variable b. Some books use a different one, but I'm going to use b. So half the width of the slit is b over 2, and that has to correspond to half a wavelength so that they're out of phase. So that's lambda over 2. And so we would have, and of course this is the hypotenuse, and here is the far side from theta, the opposite side. So there's a sine theta relationship. Sine of theta would be lambda over 2 over b over 2. Well, that's the same thing as lambda over b. So that's the angle of the first minimum. Sine theta is lambda over b. The next ones are just multiples of that. All you have to do is go twice that angle and you get to the next minimum, and 3 times that angle. You'd think with a sequence like that, like twice, 3 times, 4 times, 5 times, what about 0 times? That isn't a minimum, that's the center. And so the center peak is actually a larger minimum because of that. But all the other ones are minimum. So this is how you find the minima using that formula. Sine theta is lambda over b. Let's take a look at what this curve really looks like mathematically. And I'm going to share again here to see this, because here is a graph. Here's the graph of the actual intensity as a function of angle as you look on the slit. So here's the broad central maximum that's bright, and these are the little ghosts on each side. And the 1, 2, 3, 4, those are these minima that we're talking about that we can calculate using that formula. And this is what you get with a single slit. Interestingly, in a little bit, we'll see that this is what you get with any kind of optical system. When you try to focus it down to a perfect point, you always have this kind of figure still there in some sense. You can make it very small, but you can never make that effect disappear entirely. So let's work an example just to make this clear again. So we're just wondering, how big is this figure going to look again? So stop the share, and here's our example. So we've got a single slit that's of width, 0.1 millimeters, and 2 meters away is our screen. And so on the screen, we would expect to see, you know, if you were to draw the intensity, you'd expect to see, I'm going to shade it dark, meaning light. That's where the light is coming through. Some darkness there, and then a little bit of a hint there, and something over here, a little bit of a hint there, some sort of a pattern like this. So some sort of a broad central maximum, and then it comes down to these little ghosts on either side, something like this. That's the pattern that we're trying to work out. And what we can calculate is the distance, the angular distance from the right at the center up to the first minimum, or right at the center down to the first minimum on the other side. That's what we're going to try to calculate from this. So imagine that we really do have this. I guess I haven't chosen a wavelength here. Let's imagine that our wavelength is just 550 nanometers. That's just sort of in the middle of the visible spectrum. So what do? We solve for theta here. And so theta will be the arc sine of lambda over b. So lambda is 550 times 10 to the minus 9 meters. And then we divide by the slit width, which is 0.1, but remember that's millimeters, so we better make that times 10 to the minus 3 meters. And if you do that calculation, you should come out, when you take the arc sine, with 0.31 degrees. So it's not even a degree. That's the angular difference between the center line and this first minimum on either side. That angle is 0.31 degrees. How far apart would these, what distance would that minimum be from the center on the screen that's 2 meters away? Can we measure that in some number of centimeters or millimeters up here? Well, that's a matter of sort of drawing this triangle again. So here we've got a distance of 2 meters, and we're trying to find out what is this y distance here, and the angle all the way down here is this 0.31 degrees. So what we can say is the tangent of 0.31 degrees is equal to y over 2 meters. So y is 2 times the tangent of 0.31. Making sure our calculator is set to degrees, we'll find that y is 0.011, and that's going to come out in meters because this number out in front was in meters. So that's 0.011 meters, or 1.1 centimeters. That's the distance from the center to one of the minimum. Now, if we wanted to go from one to the other one, you know, how wide, in a sense, is this whole central maximum here? If we go all the way from one minimum to the other, then the delta y would be 2.2 centimeters. Okay, now this can get even quite a bit more interesting. I want to show you just a little bit. We're not going to do a whole lot with this, but I'll just illustrate what happens when you have multiple slits that have some width to them. So this is for a single slit. Let's include more slits in here. And you get some interesting patterns. Now, I've already talked a little bit about what happens when you have multiple slits, but here is the case where when you have multiple slits that are of some width, you might get a pattern that looks more like this. So these are quite narrow slits indeed. They are 1/10 as wide as they are separated. That's what this factor of 10 means here. In other words, each individual slit is very narrow compared to the distance between them. What if we make that number smaller? Then you might get a pattern that's more like this. Now, the individual slits are 1/4 in width of the distance between them. Let's say that they're 1/10 of a millimeter, well, let's make it 1 millimeter apart. Then, so from one slit to the next is 1 millimeter. Each slit would be 1/4 of a millimeter in width. And what you see here is two effects. You are seeing still this green line is the single slit effect. That shows you kind of an overall envelope that is caused by the individual width of those slits. And then within that is the multiple slit pattern. And this pattern, by the way, is a 3-slit pattern. And you could have 4 or 5 or 6 or whatever. But if those individual slits have a certain width, that's creating this green line. And then the other bumps in here are caused by the fact that there are multiple slits inside there. And so you've got two effects happening. And we've got two different formulas. The single slit function tells us where this minimum happens down here that sort of kills everything. And the other formula that we learned first started with 2 slits, and then I used it for any number of slits. That tells you where these maxima fall. So that's what we have learned from those two formulas. If you want, you can learn even more elaborate formulas that tell you the entire curve, but we're not going to go into that at this point. Now let me just show you an example of this sort of thing. So these were these single slit patterns. Down here at the bottom in green is a 4-slit pattern, and you can see both effects. Do you see 4 slits because there's these strong bars, and in between there are 2 smaller bars in between, 2 smaller peaks between the larger peaks. And that's because it's a 4-slit pattern. But you can also see the overall envelope that's dropping things down to kind of a minimum right here and then coming back up again. So there's sort of an overall envelope that comes down to a minimum here. That's caused by the individual width of those slits. And then out here are these little ghosts on either side. Here's one, and there's sort of the next one. So there would be a minimum here and another minimum there. Over here would be a minimum, and here would be a minimum. Those minimums are caused by the single slit width. And if we had all the numbers, we could calculate something using those. We could determine the size of the slit, for example. And then from the spacing of these, we could determine how far apart the slits are. That's what would govern that.